In this last video on logic, I would like to talk about not just mathematical statements, but quantified mathematical statements. Now, in order to do this, we're going to need to take a little bit of a journey and a refresher course in set theory. So what I'm going to do is be thinking about capital X as some sort of set and little x as an element within that set. That's what this notation means right here. And we're going to let P be a statement that can be made about the elements of X. And that'll all become a little bit more clear when we start working an example next up. And in fact, because we want to make it clear that our statement is dependent upon this variable X, much like when we are using notations in maybe like a calculus or even a pre-calculus course, when we have y equals mx plus b, we could also write that in the same way as f of x equals mx plus b to sort of stress that the output is a function of x. We're going to start doing the same thing with our mathematical statements. Instead of p, I'm going to be writing p of x. So let me introduce that example just to show you what I mean. And here I'm going to be working with a set of objects that is not necessarily mathematical things, because remember, this logic that we're studying is very universal and is meant to apply to a wide range of settings. So my set X in this example is going to be a collection of types of birds: flamingos, ducks, eagles. And my statement P is going to be a statement about the types of things that live in the set. So my statement P will be a statement about birds. And I want to think of it like a function. The statement P of x is going to be the mathematical statement, this bird can fly, but I'm going to change what bird I'm talking about. So P of flamingo would be flamingos can fly, or this flamingo can fly, however you'd prefer to think of it. P of duck would be ducks can fly. P of eagles would be eagles can fly. It's in that sense that we're viewing this statement as a function. It's a statement about the types of things that live in the set X. Now, it just so happens that with this particular set X, each and every one of these birds can fly. And so we might wish to say a much stronger statement rather than just flamingos can fly, ducks can fly, eagles can fly. We might wish to say something like all of the birds in the set X can fly. Now, we already have the tools for doing this. Using this notation, thinking of this mathematical statement P as a function of the bird that comes in, if we were to enumerate the elements of X to be x1, x2, and x3, x1 flamingo, x2 duck, x3 eagle, we could say P of x1 and P of x2 and P of x3, which roughly translates to all birds in the set X can fly. What we would be saying here with this expression is flamingos can fly and ducks can fly and eagles can fly. And because those are all of the elements of the set X, this is roughly equivalent to all birds in the set X can fly. However, writing it out this way is a little cumbersome. And because we're just doing a very small example for learning purposes, the set X is very small. If the set X had 15 different birds in it, we'd need to write out this conjunction of 15 different statements, and that would be really cumbersome when it's very brief in English to say all birds in that set can fly. And so that's the purpose of what's called a universal quantifier. So this is a mathematical symbol. It's an upside down A, and the A comes from the word all. When I see this mathematical symbol, the upside down A, I read that out loud as for all, or it's also acceptable to say for each or for every. So an alternative way for this example of writing P of x1 and P of x2 and P of x3 would be to say upside down A, little x in x, statement P of x. And the way that I would read that more naturally in English is to say, for every element of the set X, the statement P of x is true. That's the way that I would read that a little more naturally. And then if I interpret in the context of exactly what the set X is and what the statement P is, what I would be saying is, for all of the birds in my set, those birds can fly. So those are the different levels of notation and translation we experience with universal quantifiers. So universal quantifiers are for when we're trying to make statements about all of the elements of a set having a particular property. But that's not always a thing that we want to say about our set. Sometimes we want to make a different type of statement about what's going on with some of the elements in a set. So same setup as before, except I've changed my set X a little bit. Now instead of being a flamingo, a duck, and an eagle, my set X is a flamingo, a penguin, and an eagle. And my statement is exactly the same. It is no longer true to say that all of the birds in my set X can fly. A more accurate statement about this particular set X would be that some of the birds in my set X can fly. Again, I could do that with the tools that I previously have. I could use or statements instead of and statements to say either flamingos can fly, or penguins can fly, or eagles can fly. And if that statement were to be true, then we would know that at least one of the birds in my set could fly, and that's roughly equivalent to saying some birds in the set can fly. There is an example of something that does that. Again, that's cumbersome as the set X increases in size, and the translation is a little bit rough. So in order to say some of the birds in my set X can fly, or some of the elements of my set satisfy property P, we can use a different type of quantifier called an existential quantifier. This symbol uses an E, this time a backwards E because an upside down E would look like a normal E, but we use a backwards E to denote our existential quantifier, and we read it out loud as there exists or there is. So an equivalent translation to what's written here that's much more concise and that flows off the tongue a little bit better to describe the property we want about our set X is written down here. And I would read this out loud generally as there exists an element in my set for which P of X is true. And interpreting to our example, I would say there exists a bird in the set X such that that bird can fly. Now notice how forgiving that existential quantifier is. In fact, 2 of the birds in my set X can fly, and so we're being a little bit weaker here. We're saying at least one of the elements here, the property P of X is satisfied, but it could be the case that more than one of those elements satisfy the property. We're just claiming something a whole lot weaker.